Understanding nuclear fusion. What if we could harness the power that fuels the stars and bring it to Earth? In today's video, we're diving into one of the most exciting and promising fields of energy research, nuclear fusion. Imagine a future where we have clean, limitless energy without the harmful emissions and waste associated with fossil fuels. It sounds like science fiction, but it's becoming more and more of a reality. From how fusion works, to the incredible breakthroughs being made by scientists around the world, we'll explore what fusion energy is, how it could transform the global energy landscape, and why it's being hailed as the ultimate solution to our energy problems. So buckle up and get ready to take a journey into the heart of the sun and discover how nuclear fusion could be the key to a sustainable future. What is nuclear fusion? Nuclear fusion is the process by which two light atomic nuclei, such as isotopes of hydrogen, deuterium, and tritium, combine to form a heavier nucleus, releasing an enormous amount of energy in the process. This is the very same process that powers stars, including our sun. Energy release. The energy released by fusion is far greater than that produced by chemical reactions, like burning coal or gas, making fusion a potential powerhouse for future energy production. Why is nuclear fusion important? Clean and limitless energy. Fusion promises a clean, virtually limitless source of energy, producing no long-lived radioactive waste and carrying no risk of runaway reactions, unlike nuclear fission reactors. It offers a potential solution to the world's growing energy demands while mitigating environmental and geopolitical issues tied to fossil fuels. The history of nuclear fusion. Early theoretical foundations, 1920s-1930s. The idea of nuclear fusion was first theorized by Hans Bethe in 1939, who explained how stars generate energy by fusing hydrogen into helium. Early 20th century breakthroughs in quantum mechanics and relativity laid the groundwork for understanding atomic interactions, leading to the theory of fusion. First experimental attempts, 1940s, 1950s. Post-World War II, efforts to harness nuclear energy shifted to fusion. The discovery of deuterium, heavy hydrogen, fueled early experiments aimed at achieving fusion on Earth. The first fusion experiments in the U.S. explored ways to heat plasma to extreme temperatures, using devices like the tokamak, a donut-shaped magnetic confinement device. Advancements in tokamaks, 1960s-1970s. In 1968, the Soviet Union developed the T3 tokamak, the first successful magnetic confinement device for fusion. It demonstrated that powerful magnetic fields could contain and stabilize plasma, the state of matter in which fusion occurs. The 1970s and 1980s saw efforts focused on raising plasma temperatures and pressures and refining magnetic confinement systems. The key challenge during this time was reaching the break-even point, where the energy produced by fusion matches or exceeds the energy required to sustain the reaction. The ITER project and international collaboration, 1980s present. By the 1980s, international collaboration took off, with projects like ITER, International Thermonuclear Experimental Reactor, in France. ITER aims to demonstrate that fusion can produce more energy than it consummates, a crucial step toward practical fusion energy. ITER is designed to produce 500 megawatts of power from just 50 megawatts of input power, representing a major milestone in the fusion energy race. Current capabilities and challenges of nuclear fusion. Fusion technology today. Key players and facilities. ITER. As of now, ITER is the world's largest fusion experiment and remains the most significant step toward practical fusion energy. It's expected to be operational by the mid-2020s and is a magnetic confinement fusion device. ITER uses powerful magnetic fields to stabilize plasma that can reach 150 million, about 10 times hotter than the sun's core. Tokamak and Stellarator. While the tokamak remains the most researched design, the Stellarator is a competing design that attempts to solve some of the magnetic containment issues associated with tokamaks. Laser fusion, NIF. Another approach is inertial confinement fusion, using lasers to compress and heat fuel pellets. The National Ignition Facility, NIF, in the U.S., uses this method in an effort to achieve fusion ignition by concentrating powerful laser beams onto small hydrogen fuel targets. Energy break-even versus net positive energy. The break-even point, where the energy produced by fusion equals the energy needed to sustain the reactionis, a crucial milestone. The ultimate goal is to achieve net positive fusion, where the energy produced exceeds the energy input. While this has not yet been achieved, progress is being made, especially with ITER and NIF. Current challenges: plasma containment. Containing plasma at the extreme temperatures required for fusion is a major challenge. Any instability can cause the plasma to cool down, halting the fusion reaction. Materials. Materials used in fusion reactors must withstand intense heat and radiation, a challenge that researchers continue to tackle. Sustained reactions. For fusion to be viable, reactions need to be sustained over long periods, which requires constant input and precise control. How nuclear fusion works. The basics of fusion. Fusion happens when two light atomic nuclei, typically deuterium and tritium, collide with sufficient force to overcome their natural repulsion, due to the Coulomb force. This occurs at extremely high temperatures, millions of degrees, causing the nuclei to fuse and release energy in the form of light and heat. The equation. The fusion process follows Einstein's famous equation, EmC2. Even a small amount of mass difference between the reactants and products yields a vast amount of energy. Fusion fuel. The most commonly studied fuel for fusion is a mixture of deuterium, an isotope of hydrogen, and tritium, a radioactive isotope of hydrogen. Deuterium can be extracted from seawater, while tritium can be produced inside the reactor. Types of fusion devices: magnetic confinement, tokamaks, and stellarators. These devices use powerful magnetic fields to keep hot plasma suspended. The tokamak is the most researched fusion device, while the stellarator seeks to improve upon tokamak designs by offering better plasma stability. Inertial confinement, laser fusion, uses intense laser beams to compress fuel pellets, forcing them to fuse. This technique is employed by facilities like the National Ignition Facility, NIF. The future of fusion energy. Commercial fusion power plants. While fusion energy is still in experimental stages, several private companies such as Tokamak Energy, Commonwealth Fusion Systems, and Helion Energy are working to develop smaller, more affordable fusion reactors. These companies hope to bring fusion energy to market within the next few decades. Environmental impact. Fusion offers a clean alternative to fossil fuels, producing no greenhouse gas emissions and very little radioactive waste. The raw materials for fusion, like deuterium from seawater, are virtually limitless. Additionally, unlike fission reactors, fusion does not carry the risk of a nuclear meltdown, making it a safer energy source. Why use nuclear fusion? Abundant and clean energy. Fusion could provide an almost unlimited supply of energy without the pollution and environmental degradation associated with fossil fuels. It could reduce or eliminate the need for oil, gas, and coal. Energy security. Fusion energy doesn't rely on finite resources or geopolitical instability like oil or gas, ensuring a stable and secure energy future for all nations. Global collaboration and innovation. The pursuit of fusion energy has spurred international collaboration, pushing the boundaries of scientific research, engineering, and technology. Long-term sustainability. If realized, fusion could become the ultimate energy source for the 21st century, offering sustainable energy for homes, industries, and transportation worldwide. Conclusion. A glimpse into the future. The world is closer than ever to unlocking the potential of nuclear fusion as a practical, sustainable energy source. While commercial fusion power plants may still be years away, the progress being made today is unprecedented. Fusion has the potential to transform industries, including agriculture. Energy-efficient, clean fusion-powered systems could revolutionize farming, supplying clean water, powering greenhouses, and creating sustainable fertilizers. As the technology advances, fusion could become the cornerstone of a sustainable energy future, offering unlimited power for generations to come. In summary, nuclear fusion mimics the process that powers stars, combining light atomic nuclei, like deuterium and tritium, to release vast amounts of energy. Though achieving the required conditions for fusion is challenging, once mastered, it could offer clean, abundant, and sustainable power for the entire world. As we've seen today, nuclear fusion holds incredible potential to transform the world's energy systems. While there are still challenges to overcome, the advancements in fusion research are pushing us closer to a future where clean, virtually limitless energy is a reality. The road ahead may be long, but the promise of fusion power, with its abundance, safety, and sustainability, could be the key to solving some of the world's most pressing challenges, from climate change to energy security. So, whether you're a scientist, an energy enthusiast, or just someone curious about the future, one thing is clear. The age of nuclear fusion could be just around the corner, and it's an exciting time to be part of this energy revolution. Thanks for watching, and if you found this video informative, don't forget to like, subscribe, and hit the bell for more videos on groundbreaking technologies that are shaping our world.